morning, everyone. Um, this is usually the time of the weekly meeting, um, and so we will drop the link to the Discord into the chat. Okay. Yeah, this is. Uh, let's just retweet this for remember. Um, ha! That's hilarious. Okay. All right. Join us. And what is this? Okay, the video has changed. All right. And so this peer DID stuff. All right, are we going? We're going. Okay. So let me just leave that open. Okay, so this peer DID stuff, I think we opened this um, tab yesterday, and this is talking about this other thing called the DID, the peer DID method spec, and I believe this is what we want for relating parents. DID-COM approach. Okay, so they're going to leverage DID-COM to facilitate peer DID. So they're going to ride on top of DID-COM. So the first thing I always do is read the security considerations. Section is non-normative. Perspective uses a protocol rather than a public oracle as a root of trust. This protocol reliably communicates data about peer DIDs and peer DID docs. Fantastic. Peers must persist that data into local cache or database that functions as a decentralized identifier registry for the method. This method is worthy of trust because it guarantees the following properties. DIDs are associated with exactly one inception key at moment of creation. This prevents a category of man in the middle text where attacker could rotate a DID keys at the outset of the relationship unbeknownst to the peers. It also prevents any party other than the holder. Yeah, yeah, a holder of the inception key from using the DID in an unintended context. DIDs have an acceptable level of uniqueness. This is not a guarantee that DIDs will ever be improperly reused by their owners. Hello. Cool. Thank you. Oh, because this wasn't coffee. Ah, this was rasa. Awesome. Okay, yeah, coffee would be great. Yeah, that'd be great. Thank you. Sure, thank you. Okay, so um, this is not a guarantee that DIDs will never be improperly reused by their owner. Okay, because we're basically dealing with keys here. We are dealing with keys, so basically, be responsible with your key management if you're going to do it yourself. That's kind of a iffy proposition. Um, Nor is it a guarantee that collusion cannot subvert uniqueness. Thus, it is not a new uniqueness upon which deep trust can be based. Rather, a guarantee that good behavior will not produce accidental collisions. In this sense, it is a bit like the uniqueness offered by natting mechanisms in IPv4. It provides enough uniqueness that a DID can be used as an index in a database or as a routing target in DID communication. This is exactly what we were looking for. Um, it also makes it possible for blockchains to graft a peer DID by mapping it into their namespace without incurring the risk of ambiguity. Anytime a peer is discovered to be less than unique, a true problem exists in systems can fairly raise an exception. Values of DIDs are securely random. Okay? This prevents attackers from discovering patterns in DIDs that might undermine privacy. Parties to a relationship can prove the orderly and authorized evolution of their keys to one another in an unbroken chain of custody stretching back to the moment of inception. Wonderful. DIDs cannot be registered with any peer or any grafting ledger contrary to the wishes of the DID controllers. A peer DID can be shared out of context. So basically, we're gonna say, um, here's these asymmetric keys. Um, if you want to use them, uh, they have to be signed by each other. Thank you. Is it boiling hot? Okay. Thanks, baby. I love you. Okay, so this is perfect. In centralized system, security is enforced at the center, so it is so obvious we take it for granted you can't access a database unless you log into it first. It's a database that enforces this. Despite other decentralized features, blockchains are no different in this respect. If a blockchain accepts updates to a DID doc, then the blockchain must guarantee that those updates are only made by authorized parties. So this is to combat people putting stuff on the blockchain that you don't want them to be putting on the blockchain, like in your name, um, is my understanding. So basically, if you want to say, hey, this is related to that, you need to get permission effectively by getting the thing you're saying something is related to and having it sign it and say, yes, okay, yes, I agree to be related. Hmm. Data storage. Any grafting ledger. Okay, so what's a grafting ledger? Because peer DIDs are globally unique at the moment of creation, their numeric basis will not exist on any other blockchain unless someone copies it there. Blockchain-based DID methods can therefore redundantly register a peer DID doc using their own method. This process we call this process grafting. Grafting might be useful when a peer DID needs to be accepted as the submitter or target of a transaction on a blockchain. When a blockchain is used as a dead drop for a peer DID, it's important to use existing DID tools that consume a global source of truth, e.g. the DIS universal resolver in other circumstances where a peer DID is some form of partially public reference. So this is exactly what we're getting at. This is exactly what we're looking for. um, so grafting can be done in several ways by combining another DID's method prefix with a peer DID's encoded NSI. Okay. So we swapped out the namespace here, I think, or maybe that's not. Maybe that's the name. Okay, by creating a child namespace for the peers beneath the other method. Okay. this? No, XYZ. By re-encoding the numeric basis of the pure DID, we'll make this bigger. So let's check out the numeric basis of the pure DID using rules of another method. Here, XYZ method encodes base64 but encodes the numeric basis differently. There are pros and cons to each approach. If a pure DID is registered and grafted into another DID namespace using any grafting method, the result is two DIDs with different. If a pure DID is registered and grafted into another DID namespace using any grafting method, the result is two DIDs with different namespace, one pure and one anchors, each with its own DID doc. A decision must be made about which DID is normative for the relationship, or whether both should continue to be used. If both will be used, it should be understood that two DIDs hold keys and other data for two different DIDs, regardless of the shared history of those DIDs. Ideally, there would be no difference between the DID docs stored in each place, but even with the best intentions of the DID controller, differences may arise. So this is why you need to store like some kind of value that allows us to verify the data that's off chain. At least that's my understanding. Basically, so, and this is why the manifest, um, the manifest um, uh, section of the documentation on building manifests talks about requirements, or no, the shim. It's the shim. Yeah, the shim. They both talk about requirements around externally data that's external to the manifest that's being referenced. And so the reason for that is, because even if you think it won't change because the URL is static, like what if the contents get man in the middle, right? Or what if the contents get corrupted? Then we need to know that we are actually, we need some like a SHA value or something to make sure that we are not going to end up with a to make sure that we're not going to end up with contents that are different than what we're expecting, because you remember all these peers and all these DIDs are basically like our giant linked list, and so the content, the value held within the linked list is not held in the linked list. It's a pointer basically, and the pointer is the manifest. Okay, let's maybe write it out, or no. Maybe that would be helpful. No, let's just wait, just to make sure. So basically, all grafting is basically, hey, we're going to take the same data and put it on a different chain somehow, right? Um, so, and when we do that, if we're going to put it on a different chain, uh, and we're not going to change, so this value is some unique value, I think that is, so numeric basis, what is this? Method prefix. Method specific identifier. The pure DID scheme is defined with the following ABM RFC. Okay, here's another RFC document. Pure DID method specification. Okay, so let's check out this list of people. Do we see any of our friends? We see a John. I don't see anybody else that I know. Oh, but this name looks familiar to us because this name is the name. Is this? I don't know what this guy's last name is because his name on Twitter is Burr. Let's see. What is his name? Daniel Burr. That's not his real last name though. Let's see. Okay. I think it's him. He seems to be everywhere. So, the, let's see. So we let's see. DID docs. Okay, so core characteristics. Introduction. So, oh yeah, we skipped right to the security concerns. Always skip right to the security concerns. That way you know immediately whether this fits your model or not, because you don't want to get too far invested in something and then start bending over backwards for insecure default behavior within your use case. So this most documentation about decentralized identifiers describes them as identifiers that are rooted in a public source of truth like a blockchain, a database, or a distributed file system or similar. The publicness lets arbitrary parties resolve the IDs to an endpoint and keys. It is an important feature for many use cases. However, the vast majority of relationships between people, organization, and things have simpler requirements. When Alice Corporation or device and Bob want to interact, there are exactly two parties in the world who should care, Alice and Bob. Instead of arbitrary parties needing to resolve their DIDs, only Alice and Bob do. Pure DIDs are perfect in these cases. In many ways, pure DIDs are to public blockchain-based DIDs what Ethereum Plasma or state channels are to on-chain smart projects. So what is this? The basics of state channels. Okay, so this is exactly what we're talking about, is that there's just not a lot of good ways to get data on and off the blockchain, right? And so this is how we're going to do it. Um, okay, all right. They move the bulk of interactions off chains, but offer options to connect back to chain-based ecosystems as needed. Exactly, right? So this is how we're going to bridge our Web 2 to our Web 3. Um, um, So basically, we're going to put a bunch of data on the blockchain, right? That's the data we're going to put on there. These are the peer DIDs, and then what are they going to do? Well, they're going to reference data that's external via the manifests, um, and the manifests we're going to encode to some, we're going to encode it in some scheme that will allow us to put it within a DID doc, I believe. Um, Peer DIDs create conditions for people. So it looks like some formal terminology may make the application of this insight to DIDs cleaner. Anywise DID, a DID intended to use for with use for an unknowable number of parties, a global public asset or some subset thereof. So pairwise DID, a DID intended to be known by its subject and exactly one other party. E.G.E.G.1 usable in the Alice and Bob example just above. N-wise DID, a DID intended to be known by exactly n enumerated parties, including its subject. A business partnership with three members might be modeled with n-wise DIDs. Pairwise DIDs are just a special case of n-wise DIDs where n equals 2. For more on n-wise DIDs, see groups in the appendices. Generally. Okay, so important. So this is what we talked about yesterday when we said what, and this is what stopped. This is what the blocking thing with chill chat was if you have a group chat and you want to add somebody to the group chat, um, then you're going to have to go re-encode all the old messages, which means that you needed, I guess the way that I had been doing it, you needed the sender to re-encode, but you could have sort of somebody else within this group chat. Anybody who had been in there who has the data could just sort of re-encode it for you. And I've been wondering, what can we do about this with like torrents? And could we use, like, is there a space for torrents here? I don't know. I'm not quite sure. I think there's some kind of intersection there that we're going to have eventually. I think maybe what we could do is we could put the data in the torrent. So if we put the data in a web torrent, so if we put the data, so if we if we put the data in the manifest and we define, because we're going to encode the data into the manifest, we're going to put it in the DID doc. We're going to put it in the DID doc. If, and this is just the data that should live off chain, right? And so, well, what does a torrent provide? Well, it provides some, integrity checks, right? That you downloaded the thing that you thought you were downloading. So, um, we're gonna, that's a good thing. That's a very good thing for us here in terms of getting more data that's off chain. So we could potentially leverage the like torrenting and web torrents for the initial stage of getting data that's off chain, because that already implies that there's some distributed network built up on that. So we can kind of take that as our default base case, is that we're going to basically assume web torrent. Um, yeah, let's assume web torrent. So if we assume web torrent, um, if we assume web torrent, then so we need our DID distribution channels. So basically, the point is that we're gonna take these DIDs and we're gonna put them in arbitrary sources, right? So you're just gonna put these things random places, and then using the sources API, right, and the data flow preprocessing APIs, all of a sudden you can start grabbing all these data from different data sources very easily, because they're all being filtered through this as the incoming source is basically rebuild my data from the DID chain, right? And then if you write your proxies to your Web 2 space as encodings to DIDs, and handling it with the granularity of the permissions thereof, all of a sudden you now have your bridges, right? And so your bridges only need to focus on, actually, all your bridges really need to do is focus on getting the data out and in of the Web 2 space that you want. And then, so we'll just write operations for that, right? So we'll just write little operations that just take data out, data in of Web 2 stuff, right? And then we will, so data out, data in of Web 2 stuff, right? And then we just have another set of operations that adds data to, anything. So basically, yeah, data out, data in, and then you encode to DIDs, and you use the same data out, data in to transmit to other sources, which you're using as the control plane, effectively. So this means you can communicate over any channel. And you can have as much out of band communication as you can build. It's just you're applying the source construct. um, but and really, when I say you're applying the sources construct, that just means that you're going to aggregate all of the different data sources that you have, and present it as if it's one, right? And so how are you going to do that? Well, you're going to traverse the network of DIDs to grab any peer DIDs that are important in rebuilding, like your GraphQL response. Think of it like that. And then you're going to get the value of those. So you can think of the DID kind of like the plugin config thing, right? So, oops, where is it? So, double context entry pattern, plugins. Okay, so this is what we're talking about here, basically. So you can think of the DID as being this object here, right? So this is, what am I dealing with? What is this thing? Okay, so I've got a piece of data, right? It's a model, lives in the model namespace. What's the unique identifier within the model, or what's the unique identifier within the model namespace? Okay, well, it's going to be something generated cryptographically, for this specific DID, and then it's going to, encode in the data in the docs section. At least we haven't read that part of the spec yet, but we're assuming that it's going to encode in the docs section this stuff here, right? And so we're going to say, what kind of thing, and this is like kind of our manifest, right? So this is and obviously we're going to flush this out. So this is going to be conformant, whatever this is, to the manifest guidance, which says, you must include schema or whatever. um, and I think, ideally what we do is, so these DID documents, So these DID documents right now are all in JSON. I would like to see some in CBOR because that's the concise binary object representation format. And uh, the folks who have been working on that have worked, very hard to make sure that you can basically do what you can do with JSON, but you can do it in this, uh, a lot. You can put binary in there, right, for one, and then for two, you can um, you can yeah, for one you can put binary in there, and for two it saves space because it's concise. So we need to write down that we have some security considerations. So um, beautiful morning. Okay, so we have some security considerations. Well, what am I thinking right now? So I'm thinking that people put too much uh, stuff on the chain because as soon as I said CBOR, all of a sudden I saw myself putting a zip file on there. Um, and I thought, well, not everybody may like that. Not everybody may not like propagating giant zip files through, right? So, uh, relay uh, size inspection on receive slash receive from. Okay, so peer DID, what did we just write? So we wrote peer DID size inspection on peer receive, pre-receive slash receive from DWN, so which is our dis distributed web node. Okay, so asks, and then we'll start this list of nice to have. So DID is CBOR. Peer DID size inspection on pre-received. Okay, so ability. So default overlays enabled, default overlay enabled, default strategic plan overlay enabled to uh, uh, not write to disk or receive to memory DIDs beyond certain size threshold. Um, can inspect, can traverse input network to determine okay, so we can traverse the input network to determine um, can traverse the input network to determine um, um, uh, system local resource constraints. Um, can update, can traverse the input. Mm. So basically, can traverse input network to determine system local resource constraints. So Mm, so you can, yeah, so you basically you can look at the input network to determine, what's sort of the, what's the last, can you do that? Yeah, what's the last, oops, what's the last created, you know, local, because you can say what's the definition, like, so say you want to go receive something from the network, and you're gonna write it out to disk, right? And this is any, and so the reason why we care about this is because you can write this in. So recently I saw something that was, somebody came around and told me, um, you know uh, I would like to, keep the size of the files written, um, to some small amount so that I don't fill up the disk. Um, and I went and I took a look at it, and I noticed that we were, um, we were just making more files. So that's not really, helpful, right? So, but we need to, we're just going to end up making another file, and that file is going to fill up the disk, right? So we need to have some. First of all, it's all well and good if like one program does that, but then what's the command line flag? Like, did the caller remember to use it? You know, maybe not. Was the collar consistent? Can I change it if I have a different environment? What if my environment is actually, more resource constrained, and, 20 gigabytes is not, the upper bound, right, of your um, your your disk space here, right? Because these are things that are config, right? And config is something that trickles down, all the way to the lowest levels, or really needs to in some instances. And the important thing about using the data flows is that, via, the introspection ability that it gives us, and the ability to relate the different data across, projects and stuff, by understanding the intent of the command line args, and therefore and so forth, we're going to be able to say, hey, anything that looks like it's capping file size, give it this value, give it this value. And what's the value? Well, the value is dependent, right? Maybe it's an output of an operation that was calculate disk size, right? And then it went and created a little, spool directory, um, uh, similar to like a telemetry, situation, so, where you may only have want to have so much information, sitting around in a little directory, getting sucked up by telemetry, right? So, you may create a partition of a fixed size, right? So this is the type of stuff that would be done on startup. It's device dependent, and then needs to be trickled down into the rest of the settings so that sort of everything can cooperate, right? Because if you don't, if you leave that setting at 20 gigabytes and you have this 100 megabyte, spool partition for your telemetry, all of a sudden one bad thing comes in, and you're toast, right? So if you set that down to, a megabyte, then you can have 100 bad things come in, then you're toast, right? So that gives you some time to react if you're in this case Alice, and you're, dynamically interacting with your environment, right? And you're detecting these anomalies, and we're going to have the ability to detect those anomalies as well. So, okay. So DID is CBOR, nice to have. Security considerations. Default strategic plan overlay. Enable to not write to disk. Receive memory DID is beyond. Can traverse input network to determine system local resource constraints. Can go through, through operations um, um, to trigger refresh of local resources. C recording for, telemetry example. Um, Great. So that's nice. So I think that's nice. And let's see what the rest is going on here. So we want to start putting something on the blockchain. we want to start putting something on the blockchain. And what we ran into last night was what are all the arguments we need to pass to this thing? But we were using DID com, so but it looks like, and I didn't quite understand that thing. I was a little bit tired, but I didn't understand what the hell we were looking at here. So handling trust on first use. Okay. So let's see. Actually, let's read the rest of this. I think we're in the security considerations. Gotta love the security considerations. Um, yeah. Just this always just the most informative sections. Because if somebody took the time to write this, usually it means that they know they 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 care, right? And once you start writing things like this, um, once you start writing like your security considerations, it becomes starts to become pretty clear when you're leaving stuff out. Whereas if you don't write it at all, then it's much less clear what you're leaving in and what you're leaving out, right? But by writing it, you sort of, any of the verbiage involves kind of starts lending itself to explaining more and more of your threat model. Which is so it's great when people write stuff down, and these and just starting getting a start at what is your security considerations. I like that verbiage, is a really good way to start on your threat model. What are the things we need to take into account? And so basically, so what's that thing? The confidentiality, integrity, availability, right? So, high level here, we're addressing some of those areas, right? So, um, basically, falling into um, these ideas around the collisions is really a grafting is sort of how you should treat your assets, right, and what you should view their trust relationships as, right, so as to protect, like ensure, like keep those guarantees on CIA. And basically these considerations help you do that, right? Because these are considerations around maintaining those aspects. So, or just around the use thereof, that if you keep these in mind, then you can effectively mitigate for these, right? So as long as we keep this in mind, right, which is once again why we talked about, how are we going to make a machine read these specs, right, which are very human language focused, and what like how would they know what to do with that, right? And why do we care about having them read the spec? Because we would really, really, really like to just go tell the computer to write some code and then not have to write any code. Um, I mean, writing code is great, but it would be better to not write any, I think. I think it would be better if the machine wrote all the code. So as long as we can, provide certain guarantees around that, right? Freedom and privacy preserving. Um, let's see. Um, I think maybe the only path to an early retirement if the machine takes over and does everything. We'll see. Unfortunately, so in centralized system, security is forced at the center. It's so obvious we take it for granted. You can't access the database unless you log in first. Okay, so basically, despite their other decentralized features, blockchains are no different in this respect. If a blockchain accepts updates to a DID doc, the blockchain must guarantee that those updates are only made by authorized parties, blah, blah, blah. Okay, we already talked about this. Thus, most DID methods imagine a blockchain parsing the authorization. Excuse me. So then, okay, look, this is critical. So then the blockchain must guarantee that those updates are only made by unauthorized parties. Thus, most DID methods imagine a blockchain parsing the authentication section of a DID doc and rejecting mischief from hackers. So what's that? That's what we just wrote. That's what we said. Basically, um, uh, we're gonna we're gonna go with like what look. I mean, so okay. So basically, this is saying, so we can implement. Okay, we're implementing anything that holds these DIDs effectively becomes a blockchain, right? So basically what we're saying is you can take the existing sources that exist, right, that we have, and you can basically make anything a blockchain and anything a bridge, right? So um, this is going to make data analysis and import export trivial. Um, so very excited. So this is just great. So, but that is why we needed to add in this consideration because we are the blockchain. Basically, by being the importer and the exporter of DIDs, if you're storing the DIDs somewhere, you become the blockchain in effect, right? Because what is the blockchain but if not immutable records linking to each other in an immutable fashion, right? So anything that holds these, which means any source that we have, which means we can use our flat file JSON stuff, which means we can use Pickle, which means we can use MySQL, which means we can bridge arbitrary across arbitrary sources. So yeah, it's going to be great. So and we can use our input network. We can use our input network so we can even ooh, this is going to be really good. So we can even create references. We can even add more levels of indirection within trusted environments depending on our the scope and the way that we threat model those environments, right? So, for example, we can use within our chat that we have, right? Um, Maybe we have an authorized list of maintainers and those maintainers using certain keywords reference certain assets, right? And we have this indirection, or maybe even not even the maintainers but anybody within the channel, right? So we could throw on via an overlay a level a level of indirection where we look up the DID based on like a word, right? So we could have a static mapping embedded into a data flow, right? Like a little YAML file that could say what when. Okay, let me write this down. So everything is a blockchain. Everything is a blockchain. All right. Well, we're beyond. We figured out what the next thing was. We were wondering, is it what's beyond as a service? It's as a blockchain. There it is. How exciting. Um, Thank you, DIDs. Okay. So, everything is a blockchain. So, can add, can, okay, for context. So, anything, operations, operations to add to put data in slash get data out slash data flows as class to implement interfaces which call operations. Operations to put data in, get data out, data flows as class to implement interfaces which call operations. Um, Thereby creating ability to transparently proxy information into slash out of Web3 space via input networks acting as bridges transparently. Okay, so basically, and then the input network, of course, input network is made from data flow as class. Okay, code input to on add, for example, on add input method encode to DID place store in source with source dot update, or let's see, actually store in source by okay, so store in source by, okay, so how can we do subclasses? Store in source input network with mid input network made from data flow as class. For example, on add input network encode to DID store in source. Okay, and we had a input network to source, right? So when we added, so basically we want to call over to the calling add method of input network defined as data flow as class, uh, defined via data flow as class. For example, add input method encode to DID store in source by calling add method of input network defined via data flow as class within. Okay, so then operation as, so data flow, so class, so operation which enters class on is a proxy for calling a class's method. Okay, so config dot obj config dot class instance. So config dot class instance, which is usually self, but we're not going to use self because that's too much overloading. So operation, which is a proxy for calling a class's method, config.class instance dot method name, okay, can be implemented via decorator. So we'll just add a decorator, which basically does similar to at op, which basically creates, so similar to extend at op to create an imp enter, which enters the class instance context if not already entered by another operation. Their operation also using class via shared config. Okay, so basically what have we said here? So we said we have these little proxies. So basically so we have the proxy to the Web 2, Web 3 environment. So and how are we, so the last thing that just happened here was important because we just tied together, so this is, I'm yay! So we just tied together, uh, this was another piece that was missing. So we were able to tie to effectively, I think we haven't gone and done it yet, but the data flows class seems like an effective method for exposing data flows via a more user-friendly API, and also allowing us to implement our our own classes within, just as single functions, and really, get the maximum amount of reuse, right? The smallest unit of reuse is a function, right? Or a routine, an operation. So we were able to get, our unit of reuse is back down to that granular level of a function if we can define things as operations. And then if we can implement our interfaces via the data flow as class, then we can basically knit together all of these different functions and use them across classes, implementations of classes, but we can share specific data as we want depending on the locality. And that also enables us to synthesize to a particular, given any particular synthesis mechanism, like, hey, go write me this thing in, go write me this thing in C. Um, it understands where your boundaries are for locality and for trust. I think we had some stuff. Ooh, I'm remembering some stuff about the origin. Yeah, so all of this stuff tells us, what kind of input validation do we apply, where do we apply it based on the locality and the trust boundaries, and we can automate the synthesis or just the interpretation of all of this, because we have all of that data around the intent of usage. So So what did we just say here? So we're basically saying, we're going to create this bridge from the Web 2 to the Web 3 space. And how are we going to do that? Well, we're just going to do it the way we're going to do everything else, which is we're just going to write little functions, little operations, right? So basically we're writing our little data collectors, right? So we went and got the ice cream data, right? And now we're reporting out, what is the, what's this we ran the operation to do the ice cream data, right? And it looked up the temperature in the city or something, right, in a particular month. And so when we return that output, so let's update this. So we're going to pop a shell here. Connection refused. What happened to the PowerShell? Forcefully exited. Heresy. Okay. Um, okay, I switched context and now I'm forgetting what we're doing. Okay. Uh, damn it. Damn it, I context switched and I lost my train of thought. Okay. Encoded DID storing source by adding method to input network defined via data flows class within. Okay, let's finish this comment. I think we were going to go show something, but what were we going to show? I can look at the playback, I guess. Input network made from data flows class, for example, on add input network encoded DID, storing source by calling method of input network defined via data as class within um, uh, 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 data flow, which uses operations to encode, to encode DID doc, encode manifest to DID doc, which when read by shim shows how to results in a system context, which is executed to retrieve the next stage, which is potentially in this case, this is the input dot value. Okay, operations to get data in. So basically, we're going to end up with something where everything is a function. I love it. I love it. I love it. Everything will be a function, and we're going to have uh, config. We're going to have traceability on the inputs so that we know what's config and what's config for different environments. And we can apply overlays so that we can say when I'm in my specific environment, then I want you to go get this secret from over here and that secret from over there. And then when I deploy it, when you want to grab some code random, like instead of grabbing some random Helm chart off the internet and then having to figure out then you go and you have to you template these things for your environments. um, Basically we're going to link in all of that data to your existing systems, right? So that you can feed in any of those config properties dynamically. And then we're going a step deeper than that, and we're actually saying, why do it just for the containers, but let's do it for all of the config available from every piece of code running within that container, right? That's what we're saying. Okay, and then I think I'm going to take a break. I have to go to the bathroom, and then we'll be back around 9 probably. So, all right, thanks. All 0 people and anybody on the recording later. Um, have a great day. I'll talk to you later.